Hi, welcome to Modern Optimization Methods. Today we will talk about the sixth part of Chapter 7, the second-order optimality conditions. Recall that at the moment we are talking about the constraint optimization problems with equality constraints and inequality constraints. And the KKT conditions we have introduced before are as follows, which we got the gradient of Lagrange function with respect to S to be 0, as well as feasibility conditions and complementarity conditions. Also require that when we introduce the constraint qualification, we also use the linearized feasible direction capital F at point X, which actually can approximate or sometimes represent the tangent cone of omega at X. Now, let's take a look at the properties of the directions in linearized feasible direction. Now, let's take a gradient, or let's make an inner product between the direction D with the gradient of Lagrange function with respect to X. Then we can see that because at optimal solution X star, the gradient of Lagrange function is 0, therefore the inner product is 0 as well. And if we do expansion to the Lagrange function, then we can get that the two terms are equal to each other, okay, because the difference of them is 0. In other words, it means that if we take direction D multiplied by the gradient of F at optimal solution X star, then this term can be expressed by the second term here, right? We rearrange them into this part. And this term, as we can see that I in active set, so we separate the equality constraints as well as the inequality active constraints into two parts, right? So why we do this analysis, and we can answer this question in the next page. Now, if we take a further look at this equation here, it actually means that for the inner product of D and gradient of function F, it can be expressed into two terms here. And if we further take a look at the two terms, then by the definition of linearized feasible direction, we can have the conclusion that for this term, it is actually 0, okay? Because for all the linearized direction, we require that D take inner product with the gradient of equality constraints should be 0. And also, by the definition of linearized feasible direction, this term should be non-negative, okay? Because lambda I is non-negative, and this term, inner product, is non-negative. So overall, we have that the sum of the two terms here are non-negative, meaning that for the linearized direction D, it is actually a increased direction for the function value f. The inner product between the two terms will be greater than or equal to 0. Now, let's take a look at the result here. So to summarize, for all the linearized feasible direction D, we have this property that this D may be a increasing direction, or we have this D transpose the gradient to be 0, okay? So there are two possible cases. One is that this D will increase the function value. Another case is that the D will orthogonal to the gradient. In other words, along this case, or for this case, if D satisfies this condition, then we have no idea whether this function value will increase or not, because such D is orthogonal to the gradient. Okay? Therefore, the second order conditions actually take care of the directions D here. Okay? So it requires or have some special properties about such kind of D. They have to control or characterize the properties of such undecided direction in order to analyze the second order optimality condition. Okay? Now, having this in mind, then we will define the critical cone, which is actually related to such undecided directions. Now, to present the critical cone, let's make some assumptions. We assume that the function f and the constants, they are twice continuously differentiable because we need to use the second order information of the two functions, okay? And we have some settings. So we assume that at x star, where x star is actually a local minimizer, and we given the linearized feasible direction f(x star). Then we have some Lagrange multiplier lambda satisfying the KKT condition. In other words, when we talk about the second order information, we already assume that x star is a local minimizer and there is a corresponding Lagrange multiplier which satisfies the KKT condition. Now, we give the definition for critical cone. So critical cone actually defined as an intersection of the linearized feasible direction, also with another property. So which property? It actually requires that for all the active inequality constraints, the direction omega should be orthogonal to the gradient of this constraint. Meanwhile, we require that in this case, the corresponding Lagrange multiplier lambda I is also strictly positive. Okay? So this direction will be the critical cone. In other words, critical cone we denote as C x star lambda star is actually related to a local optimal solution x star as well as its corresponding Lagrange multipliers lambda star. With this x star and lambda star, we can check, okay, the linearized feasible direction, and then we also pick up those directions which satisfy the second part, okay? So the intersection between the two sets will make up the critical cone. In other words, for the critical cone, it actually requires three conditions here. The first one is that for all equality constraints, we got that this direction should be orthogonal to the gradient. And for inequality constraints here, which are active inequality constraints, we separate them into two cases. One is that if the lambda multiplier is strictly positive, then we require that this direction should be orthogonal to the gradient of constraints. Otherwise, if this lambda is 0, then we only require that it have non-negative inner product. So this will be the directions in the critical cone. So you may wonder that such direction looks weird and we have no idea how it comes. So we explain this in the page here. And as we mentioned before, that critical cone actually characterize those undecided direction for function value f. Okay? Now let's take a look at why this sentence like this. Okay, so we have this remark. If this lambda is 0, as we mentioned before, for the inactive set, okay, so this is inactive inequality constraints. In this case, for this lambda, if they lies in the inequality constraints, then we have this term should be strictly 0, okay, because lambda I is 0. Therefore, this term is 0. And for this direction in the critical cone, then we do the inner product with the gradient of f. And we can see that the inner product can be represented in this term. Okay, this is from the first order optimality condition. And for this term, as we can see that we can separate them into equality constraints, active inequality constraints, as well as inactive inequality constraints. So for the inactive inequality constraints, we already showed that this term is 0. And for the active inequality constraints, we already mentioned them in the previous part that this term is actually 0. In other words, for all the directions in the critical cone, they actually characterize the undecided direction. Okay, because this direction is orthogonal to the gradient, okay, which means that we have no idea along this gradient whether you will increase or not. Now, let's take a look at an example to show what is the critical cone like. We have minimized function f, which is very simple, it's just x1. We have 2 inequality constraints. And I think you can figure out this problem in 2-dimensional space and find the optimal solution is at 0. So at this point, then we can find out the active inequality constraints, which both of the constraints, they are actually active, okay? And with this, we can find a unique Lagrange multiplier here, okay, which we can solve from the KKT condition. We can also verify the LICQ condition, okay, by making the active set and take the gradient of inequality constraints, then we get the LICQ holes. In other words, the Lagrange multiplier will be unique actually. And then we can do the linearized feasible set, okay? We can calculate the gradient of the two terms to make them to satisfy this condition. This is the linearized feasible direction. And based on this, we can calculate the critical cone. So the critical cone actually pick up points in this set, and then we look further to find out the active inequality constraints with positive lambda I, which is the second constraint. So the second constraint, we need the direction omega orthogonal to this direction. Therefore, by simple calculation that this omega transpose gradient of C2 should be strictly 0, right? Then we can see that this omega could only take the form like 0 and D2, okay? Where this D2 is actually any real number. Therefore, we can see that by taking intersection with the linearized feasible direction, then the final critical cone will be 0, the first item, and the second one should be non-negative because we have this non-negative, all right? Then for the critical cone, we can characterize the second-order sufficient condition. Now, let's make assumptions in the following. We first assume that X star is the local minimizer of the constraint problem and LICQ holds. Then we have the corresponding Lagrange multiplier lambda star, which satisfies the KKT condition. Then the second-order necessary condition actually says that for all the directions in the critical cone, we require or we have the result as this. So the Lagrange function, if we take the Heysen matrix with respect to X, then this matrix is positive semi-definite over this cone. All right? So in other words, for all the direction in the critical cone, we have this term to be non-negative. So this is the second-order sufficient condition. In other words, for all the undecided directions, they are actually positive definite directions for the Lagrange function. All right? Or they are the non-decreasing directions for the Lagrange function. Now, we have some remarks here. So this theorem actually means that if this X star is a local solution, then the Heysen of the Lagrange function has non-negative curvature along all the undecided direction, along all the critical direction. Okay, meaning that the Lagrange function, they have non-negative directions. Now let's make a brief summary about this part. In this part, we have introduced the second-order necessary conditions. So to derive the second-order necessary conditions, we actually introduce a very important definition called the critical cone. In critical cone, we characterize the undecided direction for function f. And so for second-order necessary condition, we basically need some properties about the undecided direction in the critical cone. Okay, we stop here for this part and see you next time.